see on this graph to the right shows that latency of going across nodes. That is not an easy use case for CXL, right? Like usually we think about CXL latency just accessing a pool. Here I'm using a pool to communicate with another node, which is much easier if you had a network. And CXL still beats RDMA by a big factor. It's 4x faster in latency than RDMA, and it's 10x faster than anything you can implement with super optimized TCP IP networking. So that is a huge factor that really matters in data centers today. The same idea, you can also improve that, use that to improve microservices. If you have RPCs, which typically are really, really small, really, really latency sensitive, you have a huge fan out to tons of microservices. With CXL, again, you cut your latency by a factor of 4. I earlier mentioned stranding as a big problem. The idea there, I think, is well known that you want to dynamically allocate from the CXL pool. And here I'm presenting some new data on that, where we've run some at-scale simulations where we can figure out how much memory we can actually save if we were to pool it across hosts. So the y-axis is showing that saving, the x-axis is showing the pod size, how many hosts are connected into a pod. And then the different lines show you different use cases. And noteworthy in here is the database use case, where we can show roughly a 20 to 30% reduction in overall DRAM needs in the cluster, even at fairly low pod sizes. Now, you also see kind of some funny words in there. Octopus is what I'll talk about in the next slide, is our internal prototype, how to build the CXL pool relatively cheaply. And FC means fully connected. Actually, this spelling is quite wrong on this slide, I apologize. But that is kind of the traditional way of building a pool. I'll talk about that on the next slide. And then finally, the last talk just talked about TSP. I do want to say all of these are multi-tenant use cases. There are different people, I don't know, I think Pepsi and Coke running on the same pool. You have to be able to support that confidentially and in integrity requirements. Cool. So yeah, this is the POC that we ran things on. And I know it looks like a mess, but the thing to note in here is we use a 2-ported pooling controller, and we still are able to connect 3 hosts. How are we doing this? Basically, every host connects to multiple different pooling devices. In this case, host A connects to pool 0, which connects it to host C, and host A also connects to pool 2, which connects it to host B. So that way, host A can actually share data with both of the other guys. And you don't need an expensive pooling device. Just 2 ports is enough to scale. And as you add more ports to every host, typically we're looking at 8, you actually get a much bigger system, and you can realize some of the saving scenarios I talked about before. And I think I'm actually quite out of time. Okay. We have this prototype. It's been quite important for us that we get an ASIC pooling prototype. We've previously tried things out with an FPGA that has turned out to be a little bit too slow for our applications. This has been working pretty well. All the results beating RDMA really requires you to be really fast in terms of latency. And we've been able to verify this. We've been able to try and get high bandwidth out of that tool pretty well. We've been able to fail nodes independently. So yeah, we have some preliminary results here that pooling works for us. And with that,
thank you, Daniel. So my name is Sandeep. I'm on Azure Labs. Now that we have a working POC, our next objective is to make sure we take this to deployment. And before we can get there, we need to solve 2 things. One, look at all the implementation factors as well as challenges that we need to solve to take this to deployment. And also keep in mind that we need to leverage the existing mechanisms and infrastructures that we've already implemented for memory expansion use case and build on top of it for memory pooling use case, that way we don't start from scratch. And to that end, the factors that we need to take into consideration and solve some of these challenges include, first and foremost, memory management. When you're looking at a pooled memory, allocation and deallocation of memory resources efficiently is of paramount importance, because that's really the value proposition of memory pooling. Similarly, link management. If one of the links goes down, the pool should still be available for the other hosts that are connected. So it's applicable for link as well as reset management for that. Traffic management between different hosts has to be efficient as well. There are talked about PSP, how important it is. VM level memory isolation to ensure user data is protected across multiple hosts is extremely important in a cooled environment. Performance, ensuring quality of service as well as fairness in the way you distribute the performance across different pools is important. Last but not least, fleet management in terms of how you manage the firmware upgrades, monitoring capabilities, as well as RAS is also equally important. In the interest of time, I'll double down on fleet and RAS management just to give you an overview of how we can leverage the existing memory expansion use case infrastructure and what we need to enhance further for memory pooling use cases. So if you focus on the block diagram here, the first thing I want to mention here is what we can reuse for memory expansion use cases. So an example of that is all the communication methods that we currently have built out, whether it's in-band or out-of-band, using spec defined firmware first or OS first mechanisms or out-of-band mechanisms, using CCI, all this can be leveraged the way it is. Similarly, any kind of pre-boot testing that you might do, for example, if you want to run PPR, do memory scrubbing operations, run PPR to identify any kind of errors in the memory before you allow the execution. All that can be leveraged from what you have done for memory expansion use case. Where you would need to enhance is error handling, for example. Say for instance, if you run into a DRAM bit error during execution, which host that you notify is something that you need to be careful about. Because the host that is using that memory range is exactly the host that you need to notify this bit error about. Similarly, if you are using a DIMM-based implementation and if you run into PMIC or RCD errors, then all the hosts that are allocated that address range need to be notified about the PMIC or RCD error. So those are two examples of how we would need to enhance what we would have already built up. Fleet management can be still done through a common device such as BMC. Again, you can utilize the infrastructure that you have built up. You just need to make sure all the allocation and deallocation of memory resources are seamlessly handled. That way the host interoperation is never interrupted. Because keep in mind that our objective is to maintain fail-safe mechanism through this entire pooling infrastructure. Well, with that said, here's a technology example with Astrolab's Leo memory controller. It's unique in that we can bifurcate the PCIe links into 2x8. That allows us to build a memory pooling infrastructure. And this is a representative memory pool. Obviously, it's smaller in size, consistent with the paper that Daniel authored, which is the octopus topology, where you have up to 3 hosts connecting to a memory controller, and that allows you to build a cost-effective, performant memory pool that helps us accomplish all the goals that we set out to do in the first place. Leo today can support up to 4 terabytes. That's a significant amount of pool that you can actually share per memory controller. It has been very well tested across all the major CPU as well as memory vendors. That gives you confidence in being able to deploy with it. More importantly, we provide a very flexible software infrastructure that can be integrated into your framework. And I'll expand a little more on that in the next slide. Last but not least, as I was saying, for the first generation of memory pool that the industry would want to build, a memory controller that can support even 2 ports is sufficient, and then we can enhance that by building a multi-ported memory controller that helps us achieve all the goals that we would want to achieve with memory pooling or sharing. Talking about software infrastructure, it is quite important to make sure we have all the necessary hooks, and more importantly, it's standard-based. That way, data centers wanting to deploy can leverage their existing infrastructure that they would have already had. Cosmos is that software infrastructure that we have built up. Cosmos stands for Connectivity System Management and Optimization Software Framework. It's a combination of firmware, software APIs, CLIs, as well as GUI. And what that enables you to do is all the CXL spec-defined mechanisms such as CCI can be leveraged. And on top of that, if you're using DMTF-defined mechanisms such as PLDM for monitoring, MCTP for message communication, or SPDM for security measurement communication, it will also support that in the firmware layer. That way, you don't need to reinvent the wheel. The platforms and the software infrastructure that you've already developed for the platforms can leverage what you've already built out. Lastly, in summary, as Daniel mentioned, there is a strong demand in cloud infrastructure for an efficient memory pooling infrastructure that's both cost as well as performant. There are legacy solutions out there. However, from TCO as well as performance standpoint, they don't match up to the standards that the data centers actually need. So CXL actually addresses these problems through efficient utilization of memory. It does help us achieve all the performance, security, as well as TCO requirements. And the spec actually clearly defines all the mechanisms that you can accomplish with this. Astrolab memory controller can be used for building a memory pooling infrastructure today in data centers. The CXL 3.0 spec outlines more information on what APIs you can use, what security requirements you can meet. So I would encourage the audience here to refer to the spec. Hopefully I'm within the time limit. Happy to take any questions if anyone has. Please go ahead.
So the question is about the memory pool. So many people have talked about it, but how reliable is it when the cases of viral lead poisons and the link down things are they are exercised? So do you have any data like what effects we can observe in those scenarios?
Yeah, very good question. Very good question. The short answer is that's exactly what we're doing with the POC today, which is error handling scenarios. Whether you inject a poison or you encounter a viral scenario, the objective is to make sure not all hosts get affected, especially in a viral scenario, because in some cases OSS or kernels cannot handle a viral scenario. So while we don't have the data point, that's exactly what we're working towards. Fortunately, the spec is quite well defined on how to handle all these error handling scenarios. Ideally, if you run into, say, a poison, you would notify all hosts that are allocated that address range. Obviously, that would depend on whether it's poison or viral or so on and so forth. So that's definitely something.
Point-to-point connection, right?
That's correct.
Point-to-point. If you're pulling, it affects all the hosts get affected.
That's correct, yes. Yeah, you do need to notify all the hosts, and the notification mechanisms will not change. You can still use the standard CCI commands. Yeah.
Hi, this is Rohit from Micron. I just had a few questions on the topology. Have you considered CXL switch topology as well instead of a multi-headed kind of a configuration where you are bifurcating by 16 into by 8? And the other question I had was you spoke about Fabric Manager, but where does that sit? Which host does the Fabric Manager? Because where exactly is it sitting? Because we have topology, I did not see where the Fabric Manager was, so I was very curious to know where exactly it is sitting, and to build on the question that he was talking about, like, is it the Fabric Manager that's taking care of broadcasting all the virals or poison notifications to multiple hosts? Because obviously the memory is pooled or rather shared, we don't know that. But so those are the kind of questions I was kind of getting answers to from your. So if you can throw some light on that. Thank you.
Do you want to take the first part?
Yeah, I can. Okay. The first part. Oh, was it compared to a switch? Yes.
Multi-headed versus a CXL switch configuration?
Yes. Yeah, we've evaluated switches quite a fair bit, and most of our applications are too latency sensitive for that. Basically, our latency goal for CXL is really stringent. It's like on the order of 250 nanoseconds. And that comes from the fact that we mainly look at databases, and databases just, extremely random accesses and they're extremely waiting for everyone. And the switch latency today is, a multiple of that.
I see. And in the pooling configuration, if host 3, host 1, 2, and 3 are kind of, they're also connected, I believe.
So everything is kind of, it's implicitly connected. We could go a little bit back in the slide, but basically, if host A wants to share data with host B, it would use one port, right? One CXL port. So you explicitly expose it as a separate NUMA node. So you have to be explicit where you place your data. And then if host A wants to share with host C, it uses another port and basically puts it in that CXL device. So it's a little bit of software management that has to be integrated.
And the second question I had was regarding the fabric manager. Where does it sit, and how is it kind of orchestrating all the hosts?
Yeah, I can briefly talk about it from an Azure perspective. I mean, in a cloud, there's a control plane, right? And especially in a multi-tenant scenario, you want to make sure that you have, like we call it ring zero, you have an independent path that even a compromised host couldn't interact with, right? So it's a completely backplane thing. There's a management controller that then connects to all the pooling devices. And that's how you control things. In terms of poison management, that latency and that path would be too slow. So I'm here talking about typical IP allocation and like control stuff. For poison management and for like fault, that actually goes inbound.
In that okay. And so it's broadcast messages to all the hosts in that scenario, or only the hosts are connected to multi-headed devices? Like for example, if host 1 is connected to 2, do you also tell host 3 that, hey, I have an issue with devices 1 and 2, so how does that work?
Yeah, I mean, I don't think we have the final answer for that. I don't know, Sandeep, you have some?
Yeah, so I don't have a final answer, but I've been thinking through this and I hope we had the detail of a discussion. But there has to be some level of software intelligence built into the management framework to figure out who to notify and what to notify. It's not as seamless as having a management layer that just pushes out the messages to anyone and everyone that's connected in the topology. And that is the level of software intelligence that we need to build on top of what we've already done for memory expansion in this case.
Yeah, and the reason I was asking was with the DCD feature,
Yes.
you might see that host A is requesting a dynamic capacity device on device A, and host 2 also wants to request something on device A,
Right.
but it might so happen that even if you request, if you encounter a viral scenario, you need to kind of say both the hosts.
Yep.
So,
Yeah, the coherency management between hosts is definitely a software piece that we need to figure out. I don't think the spec explicitly has anything in the FM APIs to be able to manage that coherency management for memory pooling per se. That's something that we need to think through and work on for sure.
thank you guys.
Great questions. We'll be here in the room if anyone has any other questions. Thank you.